All right, everyone. So today we are talking through geometric sequences and series. This is section 10.3. So what is a geometric sequence? A geometric sequence is one where each term after the first term in the sequence is obtained by multiplying the previous term by a common ratio. This is relatively similar to an arithmetic sequence. Instead of adding the same number every time, we will be multiplying times the same number every time. So here we can see a geometric sequence. To go from 1 to 2, we multiply by 2. 2 to 4, we multiply by 2. 4 to 8, we multiply by 2. That value that we're repeatedly multiplying by is our common ratio, and it is 2. We can take a look at the graph here. We can see that as n gets larger and larger for this same geometric sequence, our graph will appear exponential, right? We are used to seeing that shape of an exponential graph. Now, we won't connect the dots here. We'll talk about why in a minute. But what we'll notice is that if our R value, our common ratio, is positive, our graph will appear exponential. If that common ratio is negative, points will oscillate between positive and negative, and it won't have a consistent shape. You can see here I've plotted those points, and you can see that these quantities will get larger and larger at a faster and faster rate. Just like with a arithmetic sequence, we have a general equation to find the nth term in a sequence. We take the first term, we multiply it times our common ratio one less time than the number we're on. So if I was trying to find the 10th term in a geometric sequence, I would take my initial value, a1, and multiply it times my common ratio 9 times to find the 10th number. So geometric sequences are exponential functions with a domain of positive integers. Right? Because our domain is positive integers, that's basically why our line was not connected on our graph. Our sequence is simply those key points. So let's look at some examples here. In example 2, they ask us to find the next 2 terms in the sequence and then use our common ratio to find the equation for the nth term. We'll then use that equation to find the 8th term in the sequence. So what I notice here is I'm trying to figure out, what do I need to multiply negative 81 to create positive 27? Well, I know that I must be multiplying by a negative because my signs are oscillating, they're going back and forth. And 27 divided by negative 81 would get me my common ratio of negative 1/3. I can check again to make sure the same thing will happen, and again, my common ratio is negative 1/3. So the 4th term in the sequence would be found by taking negative 9 times negative 1/3, and that would get us positive 3. The 5th term in our sequence will be found by taking positive 3 and multiplying it by negative 1/3 and getting negative 1. So those are the next 2 terms in our sequence. We are now going to try to find a general equation to find the nth term. So that's going to look like a sub n, and that's going to equal our first term, negative 81, times our common ratio, which we identified as negative 1/3, raised to the n minus 1. That is our general form, and if I want to use that formula, I can find the 8th term in my sequence by taking negative 81 times negative 1/3 to the 7th. And if we were to calculate that, we would find that the 8th term in our sequence would be 1 over 27. Let's look at another example. In example 3, they're telling us that a geometric sequence has a first term of 17 and a common ratio of 2. If a to the n equals 34,816, can we find which term in the sequence it would be? Well, let's take our general form. The nth term equals our first term times our common ratio raised to the n minus 1. What do we know? Well, we know that some term in the sequence is 34,816. This will turn into a logarithm problem. All right, so as we work through this, I can divide by 17, and I would find that 2,048 would equal 2 to the n minus 1. I'm going to take the log base 2 of both sides. Remember that logarithms unlock those exponents. So if I were to take the log base 2 of both sides, I would find that 2 to the 11th power is 2048, and that would equal n minus 1. That means that our n value is 12. In other words, that number we started with, 3,416, well, that is the 12th term in our sequence. Just like we did with our arithmetic sequences, we can also find a finite, the sum of a finite geometric series and an infinite geometric series. So if I wanted to find a partial sum, right, of a known number of terms, I'm going to take my first term, a1, multiply it times 1 minus r to the n, and divide that quantity by 1 minus r. Obviously, because of the denominator, r must not equal 1. There's another formula we're going to use here. It's for an infinite geometric series. This only works in specific circumstances, specifically when our r value has an absolute value of less than 1. Right? If r is between -1 and +1. In that case, the amount we are adding will continue to get, the amount we are multiplying by is less than 1, and therefore the result will get smaller and smaller. The numbers will basically converge at some point. And the formula we're going to use there is to find the sum of a series. We take the first term divided by 1 minus r. This depends on the fact that r is a fraction or a decimal. If the absolute value of r is more than 1, our solution would diverge. In other words, there is no sum. So let's see how we can make that work. So here we have, they want us to express 0.7 repeating as a fraction in its lowest terms. Well, this would be 7/10 plus 7/100 plus 7/1000, and so forth. Well, we could write this as a sum. We could say that our first value is 7/10, and that our r value is 1/10, right? Every time we are multiplying by a smaller and smaller fraction. So we could use our second formula and say that this will equal, the sum will equal the first term, 7/10, divided by 1 minus r. Well, this would be 7/10 divided by 9/10. And through some simplification, we'll end up with 7/9. Much simpler than 0.7 repeating, and it's just a good application of that infinite geometric series sum formula. There's a couple more problems here. I think they are worth trying on your own, 5, 6, and 7. As usual, I'll pause and work through these problems and kind of explain my thought process as we go. Things to pay attention to. Do I have an infinite or a finite geometric sum? And depending on the circumstance, you may have to use a different formula. These problems all ask different things. As I said, try it on your own first, and I will explain in a moment. All right, let's see how you did. On example 5, they tell us that a union contract specifies that each worker will receive a 5% pay increase each year for the next 30 years. One worker is paid $20,000 in the first year, and what we're trying to find is the total lifetime salary over those 30 years. So first thing I notice is over a 30-year period, that is a finite amount of time, we are going to sum a geometric series for the first 30 years. Well, what do I know? I know that the first year is a $20,000 salary, so that'll be our A sub 1. Our R value, the amount we increase by each year, is 5%. We want to convert that to a decimal and write it as 1.05. Our N value here, we can see, is 30. So we're going to plug those quantities into our partial sum formula, write a finite sum, as you see here in front of you. Your calculator do the heavy lifting, and we find that after 30 years, this particular employee will have had a combined salary over those 30 years of $1,328,776.95. On number 6, they ask us to find the sum of an infinite geometric series. Well, they just told us which of our formulas we're going to use there, and we can see it modeled as 3/8 minus 3/16 minus plus 3/30 over 32 minus 3 over 64. What's happening in this sequence is that each successive term is being multiplied by -1/2. That -1/2 is our R value. Our first term is a little easier to ascertain. It is simply 3/8. That's the first number that shows up. So because we have an R value of whose absolute value is less than 1, we can use that infinite geometric series formula where we take the first term and divide it by 1 minus the common ratio. In this case, our common ratio is negative, so that minus turned into a plus, and we simplify that fraction down to get 1/4. On example 7, they tell us that we have an approximate value of a partial sum in a geometric series where we know the first term and the R value. We are basically solving for N, as you can see on the page in front of you. So I simplified. I divided by multiplied by -0.04 and then divided by 150. I was left with, I think this is probably the form we'd like best, a decimal equals an exponential function. I took the logarithm of both sides to solve that and found that my N value was 68. In other words, 50,238.14 was the 68th term in a sequence, a geometric sequence that we were adding together as a geometric series. And that wraps up our notes. You guys can move on to our practice.